You need to come into the frame.
You're live.
We're live?
So welcome everyone to one more Safari Live seminar. It's my pleasure to introduce Abdullah Giray, Yağlıkçı. So Giray is a senior PhD student here in Safari, and he's been working on some redistributed phenomena that happens in DRAM, both identifying them and also trying to mitigate them. He has several works and publications related to them. To that, in top venues like HPCA, Micro, ISCA, and DSN. And today he's going to give us a glimpse on how to efficiently and scalably mitigate such redistributed phenomena. So, yeah, thanks. And go ahead, Giray.
Yeah, thanks, Geraldo, for the kind introduction. So, yeah, as Geraldo said, we will talk about efficiently and scalably mitigating redisturbance in modern and future DRAM-based memory systems. So this is the second part of my dissertation. We presented or discussed the first part about 1.5 weeks ago. So we will go with the second part now, and I will give some more context about the general picture as well, if this works. Okay, let's see. Okay, it works now. So, as you know, in many computing systems in our daily lives, we deal with a great amount of data, and we store this data when it's in use in these chips that are called DRAMs, or dynamic random access memory. Since DRAM holds all our data, hosts all our data, then we need to be able to trust DRAM chips for reliable, secure, and safe execution. So this is another picture of a DRAM module where we have multiple DRAM chips that work in a lockstep. And within each chip, we have multiple banks, and each bank has multiple subarrays inside. And within each subarray, we organize DRAM cells as a two-dimensional array where they are internally accessed in a DRAM row granularity. So they are organized as rows and columns. To access a DRAM row, we use a wire called word line. And then when we assert this word line, the cells in the DRAM row are connected to a bit line, which then connects them to the row buffer. And then we can access data from this row buffer. So this is how a DRAM cell looks like on the right-hand side of the slide. We have an access transistor and a capacitor. So we store the data in terms of electrical charge on the capacitor, and we access it through the access transistor, basically. And there are multiple charge leakage paths in this circuitry. Therefore, it's a volatile type of memory, and we need to periodically refresh the charge stored on this capacitor to make sure that we don't lose data. And to access data in this DRAM chip, what we do first is we need to activate the row that contains data, meaning that we fetch the content of this row to an internal buffer structure called row buffer. And then we serve the column accesses from this row buffer. And when we are done with this row and we want to access another row, we first need to perform an operation called pre-charge to disconnect the row from the row buffer. Let's talk about the RowHammer vulnerability, or this is a prime example of DRAM read disturbance. So let's say we want to access data from this row called row 2 here. So we need to open this row 2, and we access data, and then we close it. Sorry. Yes, we close it. And then when we do this operation many times, we open row 2, close it, open, close. We end up seeing bitflips in row 1 and row 3, even though we didn't access this. So this is called the RowHammer vulnerability, and it's, as I said, a prime example of a DRAM disturbance phenomenon. And this is practically used today for breaking memory isolation, which is a fundamental security and reliability primitive in computing systems. Okay, so when we keep doing this, we can end up seeing more bitflips in more rows, and we can affect actually multiple rows at once. And the row that we keep opening and closing is called aggressor row, and the other rows that are affected are called victim rows. So this is similar to from our daily lives, similar to the phenomenon of the disturbance across lanes in a swimming pool. So you have a swimmer that swims in the middle lane, but it splashes water or creates waves in the water that can actually disturb the other swimmers in nearby lanes. And this is similar to what we call read disturbance in DRAM chips, and this is RowHammer. Okay, so this DRAM read disturbance has implications. It can cause data loss or corruption. It can compromise an application's correctness. It can be used to leak private information, and it can be even used to take over a computer. And there are many examples of these practical uses. So another thing about the DRAM chips is that as the manufacturing technology advances, we try to increase the chip density so that we can put more information into a smaller space. And as a result of that, DRAM cell size and cell-to-cell distance actually gets smaller, and the DRAM chips become increasingly more vulnerable to read disturbance. And as a result of this, mitigations are becoming prohibitively expensive, and we need more effective and efficient solutions. This actually attracted quite a lot of attention in both industry and academia. And in academic papers, we can see an increasing trend that study the exploits of read disturbance or circuit level characterization works that try building a more detailed and better understanding of the DRAM read disturbance. And there are also quite a bit of work in solving this. So with this, I'd like to mention my thesis statement. All this research is oriented around the statement that building a detailed understanding of DRAM read disturbance and leveraging insights into modern DRAM chips and memory controllers enable us to mitigate DRAM read disturbance efficiently and scalably. So we already talked about the first part 1.5 weeks ago, and now we will talk about the second part about leveraging insights into modern DRAM chips and memory controllers. Okay, so still to give the big picture, I'm going to mention the other works that I did during my dissertation, PhD research. The first one was we built a deeper look into RowHammer's characteristics in terms of its characteristics under varying temperatures, memory access patterns, victim cells physical location within the DRAM chip, and change in the voltage. And we also came up with solutions to DRAM read disturbance by throttling unsafe accesses, parallelizing preventive actions, and leveraging heterogeneity to solve DRAM read disturbance in a more efficient and scalable way. So as I said earlier, we will not talk about these first four, but then we will talk about the solutions. And if you're curious about the RowHammer's characteristics in terms of these aspects, then I will invite you to look at this talk that is already live streamed on YouTube, and you can access to that talk from this link. Okay, let's start with today's topic. So we will focus on three directions of solving the DRAM read disturbance. The first one is throttling the unsafe accesses. The second one is parallelizing preventive actions. The third one is leveraging heterogeneity. And so far, I covered the background and I tried motivating this research. So far, if you have questions, maybe I can take them. Otherwise, I will continue with the first work. Okay, let's go with throttling unsafe accesses. So we looked at the RowHammer mitigation approaches at the time. This is a paper published in 2021. And we classified the existing mitigation approach into 4 different categories. So the first one is increasing the refresh rate. Basically, you increase the refresh rate for all the rows in a DRAM chip so that they refresh more frequently and the attacker doesn't have enough time to hammer these rows enough so to induce bitflips. The second one is, so with scaling, we need to reduce the time between 2 refreshes. and fewer activations can fit in this window. The second one is physical isolation. So what we do is we have our victim rows or our sensitive data stored in these victim rows in a DRAM bank, and we make sure that an attacker's memory address, an attacker's memory is not allocated to somewhere physically close to these victim rows, so that if they hammer these aggressor rows, they will be too far from the victim rows to induce bitflips. And so for that, we need to put isolation rows in between, and we need to provide a large enough distance to mitigate this. The third one is reactive refresh. Here, what you do is you have an aggressor row, which is rapidly activated or hammered, and it potentially affects the victim rows nearby. So to mitigate this, you first identify which row is being rapidly activated, and then you refresh the rows nearby. And the last one is proactive throttling. Basically, what you do is you slow down the system so that nobody can hammer rows frequently enough to induce bitflips. So all these four categories suffer from either one of these two challenges. The first one is scalability with worsens RowHammer vulnerability. The second one is compatibility with commodity DRAM chips. And let's go with the first one, scalability. Okay. Yeah, there's a lag. Okay. So the thing is, experimental characterization works already show that DRAM chips are more vulnerable to RowHammer today, and it's not getting better. It's getting worse every day with technological scaling. And RowHammer bitflips occur at much lower activation counts. If you compare studies from 2014, you would see hammer counts around like 140K to induce a bitflip, while you can see less than an order of magnitude of that hammer count in 2020 studies. And also, it's shown that it affects more rows around as well. So it suggests that in DRAM mitigation mechanism, it suggests that DRAM chips are becoming more vulnerable to RowHammer today. And there are also other works that show that the deployed in DRAM mitigation mechanisms are also ineffective. So if you buy a DRAM chip that is marketed as RowHammer-safe, it is actually not RowHammer-safe. And RowHammer is a more serious problem than ever. So when we revisit these four categories, for increased refresh rate, basically what you need to do is to increase the refresh rate much more frequently. And this actually reduces the available time of this DRAM chip. For physical isolation, you need to put more rows in between so that you will provide a thicker isolation, and it will cause more capacity to your system. And for the reactive refresh mechanisms, you need to refresh rows more frequently, and also you need to refresh more rows. And for proactive throttling, you need to slow down the system even more. And I think it's clear that these mitigation mechanisms face the challenge of scalability with worsens RowHammer, because whatever we do, we either lose performance or memory capacity. Okay. If there are no questions, I'll go with the second one.
Yeah, is it possible to refresh only certain rows?
Yes, that's what we do usually. Actually, in many different RowHammer mitigation mechanisms, you basically watch how you observe the memory access patterns, and you count which row is activated how many times, and then that gives you which rows can be aggressor rows, and then you go refresh their neighbors. We will talk more about those actually. Actually, in this second one, there's a challenge that's actually challenge that reactive refresh. I'll talk about it now. So this is the compatibility with commodity DRAM chips. Let's see. So I will take a step back and revisit how we manage our memory, how we put our data into memory. So in the application level, we deal with virtual memory addresses in our programs, right? And these virtual memory addresses are translated into physical memory addresses in the system level. It's classic virtual memory that you know. And when these physical memory addresses come to a memory controller, we parse these memory addresses and we identify which channel, which rank, which bank group, which bank, which row, which column, which bit that address will point to in the memory controller. So far, these translations are visible within the processor. So there's no problem about that. But once we send these addresses to DRAM chip, internally in the DRAM chip, these physical row and column addresses are scrambled in a way. And this is proprietary information and it is not visible from the processor. So vendors means DRAM vendors apply in DRAM mapping for two reasons. The first one is to deploy some design optimizations. When they scramble rows and columns in this way, they can simplify their circuitry to provide better density, performance, and power. And they also improve yield by mapping faulty rows and columns to redundant ones. And due to these two reasons, their in-DRAM mapping scheme can include insights into their chip design and manufacturing quality. And this is something considered highly proprietary. And as a result, this in-DRAM mapping information is proprietary. And unless you have some special deal or you reverse engineer it somehow, you do not have access to this information. So when we revisit these four high-level approaches of RowHammer mitigation, actually two of them have a strong, they face a strong challenge of compatibility because so this physical isolation and reactive refresh mechanisms need to identify the victim rows for putting the isolation rows or to understand which row to refresh. And as a result, they suffer from, they are only limited to the systems that you can get this information. Okay, so this is how it happens for refresh, for example. A RowHammer attack hammers row A. You understand this, and your existing mechanism detects the attack by looking at the aggressive row activations, and it decides to refresh rows A+1 and A-1, so that you would prevent bit flips, right? But this row A+1 and A-1 can be mapped to some different locations in your DRAM map, the DRAM bank, and as a result, in your actual physical victim rows, you can still have some bit flips, even though you perform the refresh. And existing redisturbance mitigation mechanisms need to know this information to fully secure the system. So our first work that is based on throttling the unsafe accesses is targeting this challenge and addressing this challenge in an efficient and scalable way. And this paper is published in HBCA 2021 and also selected as a finalist in Intel Hardware Security Academic Award. And here is a collection of all the links that you can use to get more information about this this paper. Okay, so this is what we do in a nutshell. So BlockHammer is the name of our mechanism, and our method is throttling unsafe accesses. So a RowHammer attack hammers row A again, but instead of refreshing, we selectively slow down these accesses that target this particular row. And as a result, bit flips do not occur, and we are safe. We prevent bit flips. And BlockHammer can optionally inform the system software about the attack as well. And by doing so, it is compatible with commodity DRAM chips because it does not need to get this proprietary info, or it doesn't need to modify the DRAM chip as well. Okay, so I will move on with more details into this paper, unless there are more questions. Okay, so our goal here is to prevent RowHammer efficiently and scalably without knowledge of or modifications to DRAM internals. And our key idea is to selectively throttle memory accesses that may cause RowHammer bit flips. BlockHammer consists of two main components. The first one is called row blocker, and the second one is called attack throttler. What row blocker does is to track row activation rates using area efficient balloon filters. It blacklists rows that are activated at a high rate. It throttles activations targeting a blacklisted row. And by doing these, it ensures that no row can be activated at a high enough rate to induce bitflips. When we come to attack throttler, it identifies the threat that perform a RowHammer attack by using this tracking information that row blocker collects. And it reduces the memory bandwidth usage of these identified threats. And as a result, it actually greatly reduces the performance degradation and energy wastage a RowHammer attack inflicts on a system. Here's a little bit more detail. So this is about the implementation or design details of this row blocker component. It modifies the memory request scheduler to throttle row activations. It has two main components. The first one is blacklisting logic. The other one is delaying logic. So it blacklists rows with a high activation rate and delays subsequent activations targeting the blacklisted rows. The blacklisting component is called RowBlocker BL. It implements counting balloon filters inside. I will explain how they work. And the delaying logic is a simple history buffer. RowBlocker blocks a row activation if the row is both blacklisted and recently activated. For that, when memory request scheduler decides to issue a row activation command, the first thing it does is to ask RowBlocker, is this activation RowHammer-safe? And RowBlocker internally tests or search these two components for this row address. And if the blacklisting logic says this row is blacklisted, and if the history buffer says that this row is recently activated, then the following row activation might be unsafe. So it returns unsafe to the memory request scheduler, and memory request scheduler does not perform this row activation. Instead of that, it can perform some other memory command. So it actually doesn't stop all the memory accesses in the system, but selectively throttles or delays some of the activations. And once the memory request scheduler eventually activates a row, it basically inserts this row activation information to these two components in parallel. This is how we implement RowBlocker BL. It blacklists a row when the row's activation count in a time window exceeds a threshold. And to do so, it employs two counting balloon filters for area efficient activation rate tracking. And this is a little bit background about how counting balloon filters work and how they work in BlockHammer at the same time, actually. So, blacklisting logic counts activations using the counting balloon filters. So a counting balloon filter is actually a very simple mechanism where we have an array of counters and we have a set of hash functions. So when we activate a row A, we provide this row address to the hash functions, and these hash functions point to different counters in this counter array, and we go increment those counter values. And then when we activate another row B, we again provide the row B's address to these hash functions, and it also points to another set of activation counters, and it also increments those. And as you can see here, some counters can be shared across different rows. And as a result, a row's activation count can be observed as more than it actually is. So we call this case false positive. And when we test row A's activation count, for example, we look at all these counters, and then we get the minimum value out of them. And since every time it's activated, it increments all the counters, the minimum value actually gives us a good estimation of the row activation count, and it cannot be observed less than it actually is. So there are false positives, but there are no false negatives. What this means is that we identify an aggressor. If we identify if a row is an aggressor row, if the activation count is high, we always detect this row, and we sometimes detect some rows that are not actually with a high activation count, but we think that they are high. But this is okay because it doesn't cause any bit flips. And since we keep incrementing these counters, they can eventually saturate. And to avoid that, we periodically reset them with to not lose information, we use two sets of these filters in time interleaved approach. So we basically employ two counting balloon filters, and any row activations inserted in both filters. Only one filter responds to the test queries at a given time, and the active filter changes at every epoch. So this is a cartoonish explanation of how this mechanism works across time. So we have different epochs. At the end of each epoch, we reset one of these filters. So we see two filters here, CBF-A and CBF-B, quantum balloon filter A and quantum balloon filter B. And these green bars show that balloon filter is active for that time period, and the gray ones are meaning that balloon filter is passive at that time. So in the very beginning, let's say CBFA is active and it does not blacklist the row for the first some number of activations. So for the sake of this example, we will assume that in the first two epochs, we assume that the row is activated at a high rate, and then later on it's not at a high rate. Okay, so yeah, so this blue box means that the rows counters are below the blacklisting threshold, so we do not blacklist this row in this time window. And since the activation count of this row increases during this time window due to the high activation rate, at some point CBFA's counters reach to the blacklisting threshold and it's blacklist row. After this point, the row is blacklisted. So all consequent activations to this row will be delayed with a certain time period. And at the end of this epoch, we reset this filter and we move to the other filter. But since both filters are trained all the time, we already have this row blacklisted in the beginning of the second epoch. And it continues being blacklisted. And at the end of, during which the CBFA's counters can also exceed this blacklisting threshold if the row is being activated in a high frequency. And at the end of second epoch, we move back from B to A. And when A becomes active again, it keeps the rows blacklisted. It keeps the row blacklisted. So we do not lose any information with this time interleaving approach. In epoch 3, we do not have frequent row activations targeting this row. As a result, the CBFB, while it's passive and being trained, its activation count for that row does not exceed the blacklisting threshold. And as a result, eventually when the filter B is activated again at 0.6 here, the row is not blacklisted anymore. Okay, so this is how it works. To ensure that, this was only for the blacklisting part. So we identify which row is blacklisted. And now we need to take an action on this row to limit its activation rate. And this is how we do that. The activation rate is RowHammer-safe if at a given time window, we perform activations less than some threshold. And this threshold is defined based on the time window and based on the vulnerability level of that DRAM chip. And to do that, RowBlocker limits the activation count in a balloon filter's lifetime. So within each epoch, or each 2 epochs, we know that the maximum activation count cannot exceed some certain level. So within each epoch, we ensure some maximum activation rate. And when you add these epochs back to back and reach to a refresh window, for example, you do not have enough activations to induce bit flip as a result. And there's some mathematical formula. I'm not gonna go through that, but you can check the full paper to understand it more. Okay, so this is the job of, so to limit the row activation rate is the job of this row blocker history buffer. And how it works is that within this time window, we have a budget of row activations. This is the NCBF here is the maximum number of activations that we can perform there. And in the very beginning, until the row is blacklisted, we do not interfere with the memory accesses, so they can be performed as fast as possible. And there can be many activations back to back until we reach the blacklisting threshold. Once we reach the blacklisting threshold, we have a remaining time in this time epoch, and we have a remaining budget of activations, and we evenly distribute these budgets of row activations in time. And for that, we basically enforce a certain delay between 2 activations. And this history buffer stores the history of row activations for this time window. And once you ask this history buffer if this row is recently activated, if you find a record of being activated, then it means that it is activated in less than this time window, and as a result, the activation is delayed. Okay. So it ensures no subsequent blacklist row activations performed sooner than T delay, and it implements a history buffer for row activations that can fit in T delay. This is just like what I explained already, actually. And the row activation is blocked as long as we make sure that this T delay is passed between 2 activations. And as a result, no row can be activated at a high enough rate to induce bit flips. The second part.
I have a question.
Yes.
Maybe I should. So, since you have some approximate count going on over there,
Yes.
you have some false positives, right? So you will blacklist some of the row accesses that are not aggressive.
Yes.
So it will have an effect on performance, right?
Definitely.
So did you consider, I don't know, applying other different hash functions? Right now you are using counting Bloom filters, right?
Yes.
Did you evaluate other hash functions?
So,
and how they
counter Bloom filter actually doesn't mandate a particular hash function. You can put whatever hash function you want over there. To make it low cost in terms of chip area overhead, we put these H3 class hash functions, which is basically just shift and XOR operations, right?
Yeah.
And as a result, we have some like we didn't minimize the false positive rate because of choosing these hash functions, right? It was just a trade-off that we did at that time. So you can implement the same mechanism using more sophisticated hash functions as well. If you go with a SHA, for example, then maybe you can have lower false positive rate. It's we didn't fully like explore that design space in that work, but yeah, I think that can help actually making this work more scalable.
Another point is that have you tried different data structure other than counting Bloom filters to approximately count? Or I don't know, one thing that I came into my mind is count min sketch.
Yes, so yeah, we did not do that. Yeah, so we
chose it because it's area efficient as well as it has enough performance gain, I guess.
I think it needs to be evaluated.
I see.
Yeah.
Another thing maybe I can ask is, so you have 2 counting Bloom filters, right?
Yes.
It's like in one epoch, one will take the action, the other one is just observing or getting
it's
the
been trained.
yes,
Yes.
it's statistics basically or something. So what if you so maybe I couldn't catch that part. What if you use just only one counting million filters with addition of, I don't know, some counter bits that, yeah, this is already blacklist. You're not gonna reset it, I don't know, into epoch period or something like this by using like some shift registers or something.
So the counters are shared across all rows, right? So
Yes.
we do not reset it based on like a particular rows being blacklisted or not. If that's the question. If we don't use two balloon filters but just one, once we reset counters, then we lose the information about the previous epoch. And in that case, an attacker can, in theory, craft an access pattern that hammers a lot until the counter is being reset, and then after reset, starts hammering a little bit more, and then you will not have the information about the past, and you will not blacklist. So we need to convey that information across time somehow. That's why we do time interleaved approach here.
I see. Okay, I thought that maybe like adding one bit that just store when you reset the counters, you'll get the information that it should be that list for the another epoch as well. Make this that bit one, and then after every end of the epoch,
So basically, you want to extract the list of rows that are blacklisted in that epoch, and then keep them in somewhere.
Yes, or just add one bit.
One bit to where?
In every counters or every counter side that it's okay, so okay. Now I understand. Okay. Yeah, it's more area efficient model. Okay.
Yeah.
Yes.
Well, we can use another balloon filter structure actually. Instead of a counting balloon filter, we can have just a balloon filter for the blacklisted rows, right?
I see it. Make it okay.
Then like every location pointed by hash function is just like one bit.
Yes.
Instead of like, I don't know, 10 bit of counter. So that can work actually as a good optimization.
But again, maybe it will increase the false negatives as well. Maybe you'll
no. There will not be a false negative, but I'm not sure how false positive rate will change.
Sort of false positive. Always forget about.
Can I ask something related to that?
Of course.
Can you hear me? Okay.
Yes.
So let's say that we have that sort of like bloom filter to get the list that are basically blacklisted. Let's say that an attacker just keeps the activation count until it is blacklisted, like just one less than the threshold. And then in the next epoch, I guess like they could still reach the RowHammer threshold. Or am I missing something?
I'm not sure if I understand completely.
So it's just making counters just threshold -1 in every reset period.
Which threshold? Blacklisted threshold?
Blacklist.
Yes.
Okay, so once it's blacklisted, you do not allow any activations for the rest of the time window. Until refresh, let's say.
Yeah, so the attacker just activates just enough to reach the threshold with one more activation and stops there. And after the reset, it keeps activating. In that case, you wouldn't know that it was blacklisted because it was not blacklisted in the previous one.
You're just talking about the when we have the balloon filter for blacklisted rows, right?
Yes.
But in that case, you would also check that balloon filter, and so that balloon filter is there to store the information about previous epoch, right?
Mm-hmm.
So why wouldn't be
like it's not like counting the activations, or maybe I just missed it.
So I think basically what she's trying to say is, so you have an epoch, like, and then
I see. Okay, now I understand.
Yes, your reset window.
Yes, your row does not get into that list, but with one more activation, it would get actually. Yes, that's true. So we're back to having time interleaved two counter filters.
Yes. So we need all the data
Yes.
in each. Yeah. Okay.
In ideal case, actually, I mean, if it wouldn't be a problem to store all this information, I guess we would go with like a counter per row anyway, right?
Yes.
So that we would have the accurate information. Yeah. Well, it's the challenge here. Thanks for the contribution, Nisa. Okay, I didn't explain this. So let's move to the second part of the BlockHammer, which is attack throttler. So attack throttler tackles the RowHammer attacks performance degradation and energy wastage on a system. And maybe I need to say a few more things about this. When you perform a RowHammer attack, you keep activating rows. And these activations are causing a lot of, it's basically stalls your other memory requests. It reduces the available time of your memory. And also this row activation is a power hungry process. It wastes a lot of energy. So we do not want to keep doing this. And what attack throttler does is that it leverages the observation or key insight that a RowHammer attack intrinsically keeps activating blacklisted rows. And it comes up with this new metric called RowHammer likelihood index. And it is basically the number of activations that target the blacklisted rows, normalized to the maximum possible activation count. And this is, again, a cartoonish picture of how this metric works. So from left to right, the metric increases. And if this RowHammer likelihood index is 0, it means that it's definitely a benign application. It does not access any of the blacklisted rows. And if it reaches to 1, this is the place where we actually reach the activation rate of a successful RowHammer attack. And the blacklisted row activation count approaches this threshold, meaning that it is definitely a RowHammer attack. And as you go from left to right, as you go higher in this index, it shows that the memory access pattern of that thread is more similar to RowHammer attack. So what attack throttler does is that it applies a smaller quota to the thread's in-flight request count as RHLI increases. So if an application is benign, no quota is applied. If an application reaches to 1.0, no request is allowed from this thread anymore. And this applies to all memory requests coming from that particular thread, not the ones only for the blacklisted rows. So it actually empties or gets rid of the memory bandwidth usage of this particular thread. And by doing so, it reduces a RowHammer attack's memory bandwidth consumption. And as a result, it enables a larger memory bandwidth to concurrent benign applications. And by doing so, it greatly reduces the performance degradation and energy wastage a RowHammer attack inflicts on a system and provides performance benefits and energy benefits. So we move to the evaluation of BlockHammer now, and we analyze 6 state-of-the-art mechanisms and compare them with BlockHammer. We calculate the area, access energy, and static power consumption of these using cacti. And we show that BlockHammer is low cost and competitive with the state-of-the-art mechanisms when you look at counter-based ones of that time called CBT twice and graphene. And these are the numbers for a RowHammer threshold of 32,000. And when we scale it down to 1,000, we observe that these overheads scale in a nicer way with BlockHammer when you look at the relative increase compared to the other mechanisms. The BlockHammers are very complex. This scales more efficiently than state-of-the-art mechanisms. And the next, we look at the performance. As Ismail pointed out, actually, the false positives is a real concern here. So we want to evaluate the performance and DRAM energy impact of BlockHammer. So for that, we conduct cycle level simulations using remulator and DRAM power for the system configuration and for several different workloads from different benchmark suites. And we also randomly choose multi-program workloads out of these benchmark suites and come up with 125 workloads, each of which contains 8 benign applications concurrently running, and another 125 workloads contain each of which contains 7 benign applications and 1 RowHammer attack. So first, when we look at the single core results, we for benign applications, of course, we see that basically BlockHammer does not incur performance or DRAM energy overheads for single core applications because they do not reach to the blacklisting threshold. Their activation counts for a row does not reach to the blacklisting threshold. Yes.
What is the RowHammer threshold?
Here we look for 32,000.
Okay.
So it's quite high actually when we think with the new data from today, right? But at that time it was actually yes, a realistic number.
Yes.
Yeah, when we look at the multi-core evaluation, we look into 2 cases. The first case, there is no RowHammer attack. 8 benign applications run concurrently. The second case, there is a RowHammer attack and 7 benign applications are running concurrently with the attack. And we look at the system through 4 different metrics here. The first one is system throughput in terms of weighted speed up. The second one is job turnaround time in terms of harmonic speed up. The third one is the unfairness in terms of maximum slowdown. And the fourth one is DRAM energy consumption. And we observed that BlockHammer introduces very low performance and DRAM energy overheads, less than 1% in both cases. And when there is an attack present, BlockHammer significantly increases benign application performance by 45% on average and reduces DRAM energy consumption around 30%, 29% on average.
What was the baseline?
Good question. Baseline is without any RowHammer mitigation.
Mitigation, okay.
So there is no defense in the baseline at 1.0, and we look at the numbers relative to that. So there is no performance overhead. There is no energy overhead in the baseline.
But how BlockHammer outperforms the
baseline?
Because
when there's attack, it throttles the attack, so that baseline benign applications in the baseline can also finish faster, right? When you have BlockHammer compared to baseline. I think I can explain it in a more convoluted way as well.
I see.
So in the baseline, nobody actually interferes with the RowHammer attack, and RowHammer attack is consuming a lot of memory bandwidth. And when we introduce BlockHammer, it actually alleviates that problem and helps benign applications to finish faster.
Okay, you increase the fairness.
Fairness among benign applications, yes.
I see.
Because RowHammer attack is a malicious threat, right? Okay. So we do not want malicious threat to consume our resources.
And here you only have 1 RowHammer attack, right?
Yes.
You just out of curiosity, you didn't check any like what happens you have 6 benign applications to RowHammer attack?
Well, this RowHammer attack is something intrusive actually in this case. It concurrently hammers 1 row in each bank.
Okay, yeah, I see.
But you can, yeah, if you have blacksmith, for example, then it needs to hammer like, I don't know, 20 rows in each bank, maybe?
Maybe. And there's a new paper in Usenix, I guess, like they're trying to RowHammer with using bank level parallelism or something. So maybe in that case, they need more cores to do that.
Could be, yeah.
Yeah.
But today, actually, for today's chips, since the thresholds are quite low, you can actually concurrently hammer like 1,000 rows, right? And reach the RowHammer threshold. And yeah, I guess 1 core is still realistic for that.
I see, yeah. Makes sense.
Okay, so the next thing we look at is how our mechanism and the other mechanisms also scale with reducing RowHammer vulnerability.
And this was again
32K, yes. And now we reduce RowHammer thresholds from 32K down to 1K on the x-axis. And on the y-axis, we again have the same metrics as before. And we again look at 2 cases for no RowHammer attack and RowHammer attack present. yeah, so we again look at system throughput, job turnaround time, unfairness, and DRAM energy consumption. And we observe that BlockHammer's performance and energy overheads remain still negligible until we go down to 1000 RowHammer threshold. And again, 1000 is actually not something that we see today with pure RowHammer attack. The lowest we see is around like 4K or 8K, something like that.
4.8K.
4.8 is for
And
double-sided
LP.
RowHammer attack, right?
Ah, yes.
In Jeremy's paper. When we introduce row press, things get bad.
Yeah, that's true.
But again, it's around 1000 if I remember, for realistic time windows. And when there is a RowHammer attack present, then we have much higher performance and energy consumption benefits as RowHammer thresholds goes down. Again, it's because of throttling the malicious thread more aggressively. We have more things in the paper. There is a mathematical security proof. There is an explanation of how we avoid or prevent many-sided attacks as well. And we also evaluate 14 different mechanisms representing 4 mitigation approaches qualitatively. And we look at them from the aspects of comprehensive protection, compatibility with commodity DRAM chips, scalability with RowHammer vulnerability, and deterministic protection. And we show that BlockHammer is ticking all those things, while the other mechanisms fail in at least one of them. Okay. Again, this is the full reference for BlockHammer, so you can find more information, and I can move to the second paper if there are no questions.
I have
Yes.
a question. So it's a throttling-based mechanism, right? So
Yes.
Does it make sense to use BlockHammer to, I don't know, combine BlockHammer with Para? Or like, imagine a scenario that you have a let's say, detection mechanism for the attacker, and you don't throttle them, you just refresh its neighbors. So does it make sense? Or
in high level, it definitely makes sense. In BlockHammer's constraints, since one of our goals is to ensure compatibility with commodity DRAM chips for this memory controller-based mechanism, we have to assume that we do not know the physical layout of the DRAM row, so we cannot identify precisely which row is next to which row. So we do not know which row to refresh.
okay, yes.
That's why we cannot combine in this space of constraints, right, in this universe. But if you have a way, let's say you expose this information somehow, or you implement Para inside the DRAM chip, so you don't have this restriction anymore because you have the information inside the DRAM chip. You can still have this kind of throttling support for those mechanisms. And that's a very good direction to go forward with like follow-up papers.
Nice. Yes.
Yeah.
Okay.
Other questions? Okay. Yeah. Are there any questions on YouTube or somewhere?
I don't know.
Okay. Then I can just move on with the second paper, right? So in this case, we move to another universe in that sense, right? We do not actually care about the compatibility problem here. We care about the performance overheads of these preventive actions that exist in RowHammer mitigation mechanisms have. So this is the paper that we will talk about. HiRA, hidden row activation for reducing refresh latency of off-the-shelf DRAM chips. This is published in 2022 in Micro, and you can find a full list of the links here. Here in this paper, our problem is DRAM refresh, because it's a fundamental operation to avoid the bitflips due to leakage and RowHammer. And DRAM refresh is one of the things that keep incurring increasingly large performance overhead as DRAM chip density scale. Our goal is to reduce the performance overhead of this DRAM refresh. And our key idea is to hide the latency of this refresh operation by parallelizing the refresh operation with other accesses to DRAM chip, so that when we perform a refresh, we do not pay for the whole latency. To this end, we propose HiRA, a new operation called hidden row activation. What it does is basically it issues DRAM commands in quick succession to concurrently open 2 rows in different subarrays, and this happens in real off-the-shelf DRAM chips by violating timing constraints. By doing so, HiRA significantly reduces the time spent for refresh operations. And to use HiRA, we also propose a new memory controller-based mechanism called HiRA memory controller, or HiRA-MC, that leverages HiRA to perform refresh requests concurrently with DRAM accesses and other refresh requests. And it significantly improves the system performance by hiding the refresh latency for both regular and periodic, both regular, periodic, and RowHammer preventive refreshes. Okay, so here's a little bit background again. So we have 2 main types of DRAM refresh in today's systems. The first one is periodic refresh. This is to address the volatility of the DRAM chip. So you periodically refresh the rows so that you don't lose data. And the second one is it's a preventive action against RowHammer attacks. So when a row is repeatedly accessed, it can induce bitflips in nearby rows. And what you do is you go refresh the nearby rows and you mitigate RowHammer.
I have a question.
Yes.
So is there any difference between DRAM refresh command and what we call preventive refresh? So I know that DRAM refresh command refreshes multiple rows at once, right?
Yes.
But is it the same as issuing act and precharge command, or do we know anything about that one?
So internally, what happens within the DRAM array is identical from a row's perspective, right?
Mm-hmm.
When you send an activation, you activate the row, you connect the bit lines, and you make your sense amplifiers amplify the signal on the bit line and restore the charge back and then precharge it. And this is exactly what the refresh does.
Okay.
And but of course, when you send a refresh command from the memory controller, it's a black box inside the DRAM chip, right? So you do not exactly know what row is being refreshed, and if there is any parallelism there. So we do not know all those.
Yes. Okay. I see. Yeah.
But in this work, actually, we do not rely on that refresh command as well. How we refresh is we send activations.
Okay. Yes. Thanks.
Sure. So as we increase DRAM chip density, now we have more capacity in our DRAM chip, and it means that we need to refresh more rows. Why doesn't this work? Let's see. Okay. Now it works. And as DRAM cells get smaller, they store less charge. And it also means that we need to refresh them more frequently. And as the DRAM chip capacity increases, based on this motivational evaluation that we have, our system performance reduces. And once we go to a DRAM chip capacity of 128 gigabits, we observe around like 26% of slowdown. And this is purely because of the periodic refresh operations. And when we look at the preventive refresh operations, RowHammer vulnerability worsens as DRAM chip density increases. And we already talked about this, more than an order of magnitude reduction in the hammer count. And when we look at the performance impact of the most scalable mechanism of that time, we observe that there is a significant 96% slowdown as we go to very low RowHammer thresholds. And that means that preventive refresh operations need to perform more aggressively, and DRAM chip dense, and they induce more and more performance overheads. And our goal here is to reduce the performance overhead of DRAM refresh for both periodic and preventive DRAM refresh operations. And our idea is to hide this refresh latency by refreshing a DRAM row concurrently with activating another row in a different subarray of the same bank. And this is our hypothesis in this paper. We hypothesize that when we activate two rows in quick succession, this row A and row B, and if these rows are located in electrically disconnected subarrays, then we can refresh one row while activating the other row. And this is how it works. So let's say we want to refresh row A and we want to activate row B. And if we wouldn't have HiRA, what we would do is we activate row A, wait until row A's charge is restored, meaning that it is refreshed, and then send a pre-charge command. And it also has its own latency. And then we activate row B, and then we can send a read command to row B. And when we have HiRA, what we do is we do this operation, activate, pre-charge, activate in quick succession. And as a result of this, we activate row A with the first activation, and its refresh operation internally starts. And then with the second activation, we activate row B. And assuming that these two rows are in different subarrays, they do not corrupt each other's data as well. And we can save a significant amount of time. Okay. So we test this hypothesis if it is true. For that, we use this DRAM bandar infrastructure that I mentioned in the previous talk as well. This infrastructure is an FPGA-based infrastructure where we have fine-grained control over DRAM commands, timing parameters, and temperature. And we test these DRAM chips. I'm not going to get into details. You can see more information about these chips in the full paper. We observe that HiRA can work on 56 off-the-shelf DRAM chips from SK Hynix, and it performs a given row's refresh concurrently with activating any of the 32% of the other rows in the same bank. So you choose a row to refresh, and you want to find another row to pair this refresh with, and then you want to activate that other row, and you cannot do it for like every other row, right? But there are like 32% of the rows in the bank that you can perform this parallelism with. And we observe that when we do this operation, we can reduce the time spent for refresh operations by 51.4%. So latency is halved here. And as a result, HiRA effectively reduces the time spent for refresh operations in off-the-shelf DRAM chips. And this is the full paper, again, for you to see more information about the characterization results. So now we move to the mechanism, HiRA memory controller. Our goal is to leverage HiRA's parallelism as much as possible. And for that, we leverage the key insight that a time select is needed to find a row activation and a refresh to perform HiRA, because we cannot parallelize every refresh operation with every activation, right? So we need to find the pairs of rows that we can perform this parallelism. And for that, what we do is, or HiRA memory controller does is, it generates a refresh request in advance in time, and it assigns a deadline for each refresh request. And there is a time select between the refreshes generated and the time that it has a deadline. And within this time select, there can be multiple activation commands happening. And let's say, for the sake of this example, row A can be parallelized with row Z. Then HiRA memory controller basically replaces activation command with a HiRA command, or activation pre-charge activation command sequence. And by doing so, it performs these operations in parallel and reduces the refresh latency, basically, or the time spent for the refresh operation. So we have a lot of details in the paper about how we implement this HiRA memory controller. It basically has the necessary hardware components to generate these periodic refresh requests and RowHammer preventive refreshes with deadline. And it buffers each refresh request and performs the refresh request until its deadline. And it finds if it can refresh a DRAM row concurrently with a DRAM access or another refresh. Again, I will refer you to the full paper for the details of this mechanism. Okay, so this is the performance evaluation of HiRA. So we again perform cycle level simulations using Remulator to see our performance benefits, and we simulate the system configuration, and we come up with 125 different 8-core multi-program workloads from Spec Benchmark Suite. And we sweep through 2 parameters. One of them is DRAM chip capacity. We increase DRAM chip capacity from 2 gigabit to 128 gigabit. And we reduce RowHammer threshold from 1024 down to 64, which is very aggressive. And let's look at HiRA's performance impact on periodic refreshes. So here on the x-axis, we have the DRAM chip capacity increasing from 2 gigabit to 128 gigabit. And on the y-axis, we look at the weighted speed of higher is better. It is the system performance, normalized to no refresh. So the first bar I show is no refresh. So in this case, we do not have any refresh. So it's very idealistic. You do not have the system. And the performance is 1.0 everywhere because it's normalized to no refresh. And in baseline, we use auto refresh, which is the refresh command that we see in the DRAM specifications. So it is the conventional way or industry standard of performing these refresh operations. And we observe that when we use auto refresh, it can cause 26% slowdown when we reach to a DRAM chip capacity of 128 gigabits. And instead of auto refresh, if we use HiRA, then we can reduce the performance overhead that these periodic refresh operations are inducing to the system. And as a result, we can increase system performance by 12.6%. Those were the results for periodic refresh. And now we look at the preventive refresh results. On the x-axis, we look at now we scale the RowHammer threshold from 1000 down to 64. This is the minimum activation count you need to perform to induce a bit flip. So going from left to right, we are going to feature. And the first bar I show has no defense. So it is, again, an idealistic system that you would want, but it is not reliable, it is not secure. So you wouldn't use this kind of system. And we choose Para as the baseline because it has the lowest hardware overhead going forward. With so in terms of chip area overhead, it's the most scalable RowHammer mitigation mechanism or defense. And we observe that as we go to very low activation counts or RowHammer thresholds, Para induces 96% of slowdown. It means basically the system is not available anymore. It doesn't work. You cannot use it. So when we use HiRA instead of Para, again, our performance is not really great, to admit. But compared to Para, actually, we have 3.7x speed up. So we have more details in the paper. We provide a lot of details into our real DRAM chip experiments, how we verify HiRA's functionality and variation in HiRA's characteristics across different DRAM banks. We look at the sensitivity of HiRA to the length of the time select for refreshes, number of channels, number of ranks in the system. And we also have a hardware complexity analysis, and we show that HiRA has very low hardware overhead. And we also provide a lot of details into our experimental methodology, and we provide the detailed algorithm to find concurrent refreshes as well. And this is the full paper again. And this clicker does not work. Okay. In conclusion, we propose HiRA. This is the first technique that refreshes the DRAM row concurrently with activating another row in the same bank in off-the-shelf DRAM chips. And through real DRAM chip experiments, we show that it works in 56 real off-the-shelf DRAM chips from SK Hynix, and it can reduce the time spent for refresh operations by half. And we propose memory controller mechanism to leverage HiRA's parallelism to perform refresh requests concurrently with other DRAM accesses and other refresh requests, and it provides significant speedups. Again, this is the full reference of the paper. You can find more links, slides, and the lecture video on this paper. Okay, this was the second one, and I'm gonna move to the third part. How are we doing in terms of time? Just 1 hour. Good. I think I will finish around like half an hour, in case you guys want to sleep. But yeah, I can stop here and take more questions if there are any.
So one question,
Yes.
Why did you choose HiRA, or sorry, why did you choose Para with HiRA? So can you did you think that like, can you combine HiRA with other existing mitigation?
So basically, you can combine it with whatever refresh-based mitigation mechanism. Right? Whatever, for what reason you use refresh, you can use HiRA for that.
I see.
We choose Para because when you look at other refresh-based mechanisms, they need to implement a lot of counters in the memory controller, and it ends up like consuming a lot of chip area when you go to those very small RowHammer thresholds, and they become basically not really practical. It's like prohibitively expensive in a way. So in Para, you only have like one register, right?
Yeah.
And it doesn't change as you go low in RowHammer thresholds. So in terms of area overhead, it's the most scalable one, and it induces a lot of performance overhead, and we try solving that here.
I see. Okay. So
we can push back more.
No. What I was thinking that you need I think a lookup table or something to, so if I'm going to refresh row A, okay, I can refresh also row Z, right? So you need a somehow table or something that you need to store those informations. So what I have in mind is that, I mean, those other mitigation mechanisms, maybe you can pair those things, right? For example, if you can concurrently refresh row A and row Z, they can share counters, so you can reduce their area overhead, and you can send activation command without any additional performance cost. Yeah, but that's a good idea actually. You can just pair them statically, and you can perform refreshes in parallel. Yes, because we already have this information. Yes, but here what we try to do is we try to parallelize a preventive refresh, let's say, with the dynamic access. So let's say you can parallelize row 0 with row 1000, and you generate the refresh for row 0, and there's a deadline, but there's no guarantee of there's an activation coming for row 1000 in that time window, right? And there are like many candidates of activations that you can do this parallelism with. Yeah, if you remember, based on the characterization results, like for a given row, we can use 32% of the rows in a bank to parallelize. I also want to ask that, but yeah. Yeah. I guess you have more insights. I know that your research is going on that direction. Yeah. But yeah, go please. You were saying. Yeah, what I mean is like it's not practical to make this like keep this or maintain this information for each row you have 32% of the other rows. It's not real practical to maintain all this metadata. Yes, that's true. Yeah. So and since our goal is to parallelize as much as with the dynamic accesses, we chose this kind of method, and we chose Para. But theoretically, if, for example, you want to perform something with a row, and you can choose any subarray that is not physically adjacent, right? You can choose any subarray, like you can choose a row from a subarray that are not physically adjacent to that rows that you're going to operate. Yeah. Right? That means that, for example, if you have 100 subarray and you're going to read from row A from a subarray, so you can use all the other rows in the 97 subarray, right?
Yes, actually,
Theoretically.
that's how we keep that metadata. Actually, we reverse engineer subarrays, and then we identify which rows in which subarrays can be parallelized with each other. So we keep that metadata in subarray granularity in that sense. So that we check like the subarray IDs of rows when we try to find the parallelism.
But that should be higher than 32% or something, right? Because
yes, that's true.
Yes,
I was also expecting that, but we did not observe reliable operation for like many rows.
reliable means sometimes you get corrupted data when you perform.
Yes, you can get corrupted data. And this is not something that is officially supported by the DRAM manufacturers. So
Yes, I see.
it's also a black box, as you're very familiar with. So it's really hard to understand like what's going on under the chips package.
Yeah, I think at least this paper like highlights that there's a potential and there's a proof of concept that you can do this operation without any cost.
Yes.
So basically, if manufacturers can actually support this, it's not like just 32%, but it's almost, it should be more than like 90 or I don't know.
Yeah, it can easily go above 90%.
Yes.
And once they officially support this, actually, they can also build very low overhead mechanisms in subarrays, in row decoders, and they can easily like parallelize all these operations internally as well, right?
Yes.
And you can pretty much hide all these maintenance operations in that way. I think there are like good works in that direction. So subarray level parallelism paper, the SALP, DSARP from Kevin Chang, they're quite good in that. Like they already like engineer what kind of circuitry you need to put there. So yeah, there is good potential over there. One contribution of this paper is that after all these years, these operations are still not officially supported, but we can see that this functionality happening in some DRAM chips today. So there is maybe partially those circuits already exist inside. So this is more motivation for official support in this and including them in the JEDEC standard so that we can leverage this parallelism.
Yes, I mean, it could be good to think about how we can combine this here and with other existing mitigation mechanisms, maybe to lower the cost.
Yes, of course. Yeah.
Thanks.
I guess, sorry.
Yeah, please.
Yeah, one good example can be Rega actually, right? So over there as well, within the subarray, you have some parallelism.
Yeah.
And it already shows that when you use this kind of parallelisms for RowHammer mitigation, you can actually achieve things for like much cheaper overheads.
Yes, like 2%. Yeah.
Yeah.
That's true.
Yeah, you keep mentioning that it was tested on 56 chips, meaning that it worked only on that, or like other chips were not tested?
Yes. We tested other chips. We tested chips from all three major manufacturers like Samsung and Micron as well. We did not observe this operation reliably working on those. Like an anecdotal evidence, I can say that, you know, in some Micron chips, there were some, I mean, partially there was some promising results, but I didn't see any like two rows that performed this operation with no bitflips. Yeah, but there were rows with like very low bit error rate.
Maybe this could be because of the difference in internal architecture.
Exactly, yes. So we do not know what they design internally around DRAM array in the I/O circuitry periphery, and they're completely free to do whatever they want to do because like this is beyond the JEDEC standard, so it's not something that they should support. Okay, thanks. Let's move for the third one. So now we want to leverage the heterogeneity that we find in the DRAM chips. So this is a paper that will appear in HBC this year in about a month. And it's called, okay, let me read the title. Can I go back? Okay. The title is Special Variation Aware Read Disturbance Defenses, Experimental Analysis of Real DRAM Chips and Applications on Feature Solutions. So again, here we have some real DRAM chip characterization study and then some architecture level work. So our motivation is that read disturbance is a worsening DRAM reliability and security problem, and existing mitigation mechanisms suffer from significant performance and energy overheads, limited effectiveness, or prohibitively high cost. And our goal is to understand the spatial variation in read disturbance across DRAM rows, and to leverage this understanding to improve the existing mitigation mechanisms. For this, we test 144 DDR4 DRAM chips from 3 major manufacturers and characterize all rows in a bank and a bank from each bank group. And we observe a large variation in the necessary activation count to induce the first bit flip. And although we do not observe any strong correlation between a row's spatial features and its read disturbance vulnerability, we still come up with this mechanism called Svärd. Svärd dynamically adapts the aggressiveness of a RowHammer defense, and it can be implemented in either in the DRAM chip or in the memory controller. Basically, we propose Svärd as a mechanism that is ad hoc with the existing RowHammer solution in your system. If your RowHammer solution is implemented in the DRAM chip, Svärd can also be with that in the DRAM chip, or if your solution is in the memory controller, it can be also implemented in the memory controller. And we try Svärd with 5 different RowHammer mitigation mechanisms: Aqua, BlockHammer, Para, HiRA, and RRS. And we show that it reduces the performance overheads of these mechanisms. And I think the slide is a bit redundant at this point. So with increasing DRAM chip density, we have RowHammer or DRAM read disturbance problem getting worse. Again, more than an order of magnitude reduction in the necessary activation count to induce the first bit flip, and it can cause significant performance overheads. So this means that preventive actions need to be performed more aggressively as DRAM chip density increases, and they cause significant performance overheads. I cannot go. This clicker doesn't work sometimes. And our goal is, in this work, is to understand the spatial variation in read disturbance across DRAM rows. And if there is any spatial variation, to leverage this to improve the existing read disturbance solutions. And for that, we use, again, the same DRAM testing infrastructure, DRAM Bender, that gives us fine-grained control over DRAM command time parameters and temperature. And we test these 144 DRAM chips. You can check the full paper for a more detailed table as well. Yeah, here is the paper, and it will be online sometime soon. And our key takeaway from real chip experiments is that read disturbance vulnerability varies significantly and irregularly across DRAM rows. So here, what we see is a histogram. On the x-axis, we have the minimum hammer count to induce the first bit flip. And on the y-axis, we have the fraction of DRAM rows that fall into that HC first value, that exhibit that HC first value. Here, different colors show different data from different modules. And all of these modules are from manufacturer M, Micron in this case. And the error bars are on the bars are showing the variation across banks.
Is this double-sided or single-sided?
Double-sided. So we observe the lowest HC first around like 8K for these modules and highest around 128K. And this means that there's a large variation in the minimum hammer count to induce the first bit flip across rows in a DRAM bank. And I showed the same plot for modules from all 3 manufacturers. The top one is SK Hynix, the second one is Micron, the third one is Samsung. And we observe a large variation in the minimum hammer count in the first bit flip across rows in a DRAM bank for all DRAM modules from all these three manufacturers that we test. Okay. And here we look at, at the moment we know that there's a large variation. So we want to understand if this variation somehow correlates with the row's location within the DRAM bank. So on the x-axis, we have the relative location of a DRAM row. So when you look at the leftmost point, 0, and rightmost point, 1, these are the two edges of a DRAM bank. And this, like the location on the x-axis just shows the relative location of a DRAM row in the DRAM bank. And on the y-axis, we have the minimum hammer count, or HC first, of this particular row. And we have this in a normalized way. And we normalize it to the lowest HC first that we observe in the DRAM bank. So this one, like on the y-axis, the 1.0 line is actually showing the most vulnerable DRAM rows. And the other points are basically having larger HC first values. And how many times? So 5, for example, means that the HC first value of that row at y equals to 5 is like 5 times larger than the minimum HC first you observe in that row, in that bank. And again, different colors correspond to different modules here. And I guess, as you can see, no visible regularity, at least to my eyes, it's not visible in HC first based on the row's location. So there are no clear patterns. There are some rows accumulated at some levels, and the variation among them seems quite irregular. And that's why we conclude that the HC first or minimum hammer count to induce the first bit flip irregularly varies with respect to row's location in DRAM bank. And this is the case for modules from Micron as well, and also from Samsung as well. Although you can see some repeating patterns vaguely in Samsung, and we actually find a little bit of correlation in Samsung modules as well, but not very strong. Yeah, okay, this is another part. So for this part, we just conclude that the variation is somewhat irregular.
So
yes.
Did you check variation in each subarray? So
I will show.
Oh, okay.
These arguments, the model suggested.
I need to double check. Okay. So I just put this slide as a reminder of RowPress paper because I will explain some experiments that we conducted for this work that are inspired from RowPress paper. So RowPress was a new DRAM read disturbance phenomenon. It was discovered earlier in 2023, published in ISCA. So we in RowHammer, we need to keep opening and closing rows. In RowPress, we open the row, we wait long enough time, and then we observe bit flips. And when you look at the access pattern, in RowHammer, you need to open and close as frequently as possible. But in RowPress, you actually open, wait a little bit, close, and then immediately after that, open again as soon as possible, and then wait again. And RowPress shows that this kind of access pattern can significantly reduce the hammer count you need to induce a bit flip. And here is what we did for that purpose. So we look at effect of RowPress on special variation of read disturbance vulnerability across rows. Again, we test all rows and the same methodology. And we check this for 3 different time windows where we keep an aggressive row open whenever we activate it. So on the x-axis, you can see that. In the leftmost one, we keep the row open for only 36 nanoseconds. This is the minimum time you have to keep the row open. So it's equivalent to RowHammer. And the second point is 0.5 microseconds, and the third one is 2 microseconds. these are some realistic values that you can reach by accessing different columns in the same row. You can force the system to keep your rows open. And this is the aggregated data from manufacturer H, SK Hynix, and on the y-axis, we look at how HC first changes. And we observe that row press reduces the mean of the distribution and also the interquartile range, and the whole distribution basically goes lower. As you can see, from purple to yellow, everything goes lower. And there is still significant variation in HC first across rows. This is important for us because we are trying to leverage this variation. And when we look at the same data across different manufacturers, we observe some similar patterns. Bitflips occur at lower hammer counts with row press, and these hammer counts still significantly vary across DRAM rows. Now we conduct some correlation analysis to understand if there's any correlation between a DRAM row special features and its RowHammer or read disturbance vulnerability. For that, we look at, bank address bits, subarray address bits, row address bits, and a row's distance to its local row buffer. And our methodology is that we first cluster DRAM rows into 15 bins based on each row's minimum hammer count in the first bit flip. And we predict whether a row is in a cluster or not based on each special feature. And we measure the F1 score for each special feature. And we look at the F1 score for these special features, basically. So on the x-axis here, we have the F1 scores, and this is a cumulative distribution function of the special features across all those bits, basically. And in the leftmost one, with like 0 F1s, so so this is a cumulative distribution function, right? So a point here at 0.1 means that let's say in the leftmost one, at 0.1 on the x-axis, we have something around 0.6, 0.7 on the y-axis. It means that 60–70% of the special features exhibit an F1 score up to 0.1. And we observe that there are few special features from Samsung that can exhibit a F1 score a bit larger than 0.7 here. But for the other ones, we do not observe anything above 0.7. So this means that there is no strong correlation between row special features and read disturbance vulnerability. And therefore, we conclude that read disturbance vulnerability varies significantly and irregularly across different DRAM rows in a DRAM bank. And with this observation, we come up with this Svärd mechanism. Our key idea is that since not all parts of the memory are equally resilient to DRAM read disturbance, we want to protect the weak more aggressively than the strong, meaning that we dynamically tune the aggressiveness of existing solutions based on the vulnerability level of a victim row. So if you attack, so we first classify DRAM rows into several vulnerability levels. For this, we maintain a few bits per DRAM row. About 4 bits is enough for like 15 classes, right? And we dynamically adapt the aggressiveness of a mitigation mechanism based on the victim row's vulnerability level. So this can be, again, applied to any given pretty much mitigation mechanism. In this paper, we tested with several of them, 5 of them. So the first one is para. For para, we adjust the probability threshold in para mechanism to adjust this aggressiveness. For mechanisms like HiRA, Aqua, RRS, we change the activation threshold. And for BlockHammer, we change the blacklisting threshold. So this is, again, a cartoonish picture of how your memory controller looks like. Excuse me. So your memory requests come from the front end of the processor to a memory controller, and there's a memory request scheduler here. And this memory request scheduler generates DRAM commands and sends the address and data as well to the DRAM chip. And in back, you get data back, right? If it's a read command, for example, you get the data back. And once you implement a RowHammer defense mechanism in the memory controller, you can abstract it in this way. It observes the DRAM commands and addresses. And based on those observations, it creates some preventive actions and injects those preventive actions to a memory request scheduler. In BlockHammer's case, for example, it forces memory request scheduler to not to activate a row. Or in Para's case, or in HiRA's case, it injects some refresh operations in the memory request scheduler. So those will be performed sometime soon. And in RRS's or Aqua's case, for example, it creates some other routines over there that move contents of data from one place to another place. But we don't have to actually get into those mechanisms because those are prior work anyway. So these mechanisms work with an HC first value. So you configure them based on the minimum hammer count that is needed to induce a first RowHammer bit flip in your chip. And the thing is, this HC first value is you have to configure this mechanism based on the worst case HC first in your DRAM chip. It needs to be tuned to the weakest row you have in your DRAM bank, right? Without Svärd. So with Svärd, we have multiple implementation options here. For this memory controller-based mechanisms, you can implement a HC first table over there that would effectively store around like 4 bits for each DRAM row. And based on the row address, you can get the HC first value and then feed it to the existing read disturbance solution, and it will perform the preventive actions accordingly. If HC first is large, it will be less frequent. If it's low, then it will be more frequent, more aggressive. Another way of implementing this is if your chip has some extra metadata bits that come when you read data, then you can maybe put this information over there as well. You can fetch that from the metadata bits. Okay, so I didn't go into details, but there's also implementations that we can discuss for on DRAM die RowHammer mitigation mechanisms. We just didn't evaluate them in this paper, so they are not in this implementation. But it's very practical and possible. So let's move with the performance evaluation. Again, we use some cycle level simulations. This time we use Remulator 2.0, which is recently published. I strongly recommend it. It's quite a nice tool to use. It's very modular. And we simulate this system, and we have 120 different 8-core multi-program workloads from different benchmark suites. We randomly compose them, and we pair Svärd with Aqua, BlockHammer, Para, HiRA, and RRS. And we sweep the HC first values from 4,000 down to 64. So we get the distribution of HC first values in a DRAM bank, and we scale it down to lower thresholds, assuming that the variation will be similar when we go for lower hammer count thresholds. And based on that, we estimate or project the performance implications of our mechanism. So this is the result for Para. On the x-axis, you see the minimum hammer count to induce the first bit flip going down from 4K to 64. And on the y-axis, we have the weighted speedup metric again, which is the system performance higher is better. And everything is normalized to the no mitigation baseline. So 1.0 means that there is no mitigation operations are going on. And we have 4 different curves in different colors. So the lowest curve, which is dark blue or purple, depending on the resolution of your screen, I guess, is no Svärd, meaning that it's the original Para proposal. And the 3 different configurations of the 3 other curves are based on So those are the results for the case where we integrate Svärd with Para, and for different DRAM modules profiles. So we collect profiles from 3 different DRAM modules, 1 from each manufacturer, and they generate these different results. So when we look at these 4 mechanisms, Aqua, BlockHammer, RRS, and Para, we observe that the performance overhead significantly increases when you scale down these mechanisms. And by using Svärd with these mechanisms, we can actually gain back a lot of that lost performance. And as a result, we get some significant speed ups around like from 1.23 to 2.76 times of speed ups for very low RowHammer thresholds when we use them with Svärd. And actually, it's important to note that, for example, for RRS or Para or even for Aqua as well, you can see that if you have a very nice distribution of HC first in your module, look at the yellow curve, for example, you can actually have very similar performance to the baseline where you have no RowHammer mitigation mechanism. So it effectively reduces your mitigation mechanism's performance overhead a lot. So Svärd significantly reduces performance overhead of existing solutions. So there is a outlier, which is the 5th mechanism that we tried, but I cannot move the slide, which is HiRA. So in HiRA's results, we again see that HiRA without Svärd is incurring a lot of performance overhead, and it's the lowest curve in the plot. But we do not see much of improvement with when it's integrated with Svärd for 3 different modules. And the reason is that, to explain the reason, I need to dive a little bit deep into HiRA and explain how HiRA works. Okay, I'm just going to use the keyboard. I think this is gone. So HiRA is a mechanism that is published in ISCA 22 from Moin Qureshi. And the key idea is to maintain a row activation counter for each DRAM row, and you store all these activation counters in DRAM array because you have the high density and it's low overhead in that sense. And to access these activation counts in a low latency, you need to cache some of them inside the memory controller to alleviate the off-chip link, right? And as you go very low in the HC first configuration, or the minimum hammer count you need to induce the first bit flip, many rows become hot. So it means that you need to cache the activation count of many more rows as the RowHammer threshold gets lower. And it means that you either need to increase the size of this cache, or you need to keep fetching and evicting counters from this cache to or from the DRAM chip. And it actually dominates the performance overhead at very low RowHammer thresholds. And definitely we need to go for like further customizations if you want to integrate Svärd with HiRA. For like higher cache configuration, higher capacity cache configurations, for example, we can mitigate this dominance of the performance overhead by fetching and evicting counters. And in that case, it's possible to observe better performance improvements. But currently, it's very low performance improvement, like around 3%. Okay, so we have more information in the paper. So we have the special variation and read disturbance in terms of bit error rate as well. We explain all our algorithms and details of our experiments. You can go check them. We have some reverse engineering data about finding the subarray boundaries. And we have more detailed results on the correlation between special features and read disturbance vulnerability. And we have a preliminary analysis of the effect of aging on DRAM read disturbance vulnerability. and this is the full paper. It will appear in HPCA. In a nutshell, in this paper, we tested 144 DDR4 DRAM chips from 3 major manufacturers and characterized all rows in a bank and a bank from each bank group. And we observe a large variation in the necessary activation count to induce the first bit flip. And we did not observe a strong correlation between a row's special features and its vulnerability, but still it didn't stop us proposing this mechanism called Svärd to dynamically adapt the aggressiveness of a RowHammer defense to the vulnerability level of the victim row. And we implement Svärd, we can implement Svärd either in the DRAM chip or the memory controller. And it reduces the performance or health of existing solutions. So this is a screenshot from HPC24 program. So we will have Svärd's presentation in the second day in session 5B. And I'm looking forward to that and to have more discussions in that talk and after that talk as well. And in the same session, we have another paper called Comet from Nisa. I think she's online now. She's proposing a very promising RowHammer mitigation mechanism that Ismail was trying to foreshadow in the earlier discussion. And we also have 2 other papers, one from Ismail in the near memory processing session in 2C, and another one from Geraldo that's really interesting as well in accelerators and memory systems. So we're expecting to see have a lot of interaction in that conference. We hope that. Yeah, so this is the end of HiRA and end of my papers as well. So I can get more questions at this point if there's any. Otherwise, I'll just move with the future directions, cover them in 10 minutes. So 30 minutes became 50 minutes, but I think this time it will be just 10 minutes, and then we can conclude. What? Do we have any questions? Okay. Okay, so future research on efficiently and scalably mitigating DRAM read disturbance. So we did a lot of stuff to understand how DRAM read disturbance happens, how it behaves under different conditions. And we also proposed several architecture level solutions to attack this problem from different angles. And but this is, of course, not the end of this research. There are more things to discover and more things to look at. We already talked about this deeper understanding of physics and vulnerabilities in the previous talk, so I'm just going to skip it. But you can refer back to that YouTube video that I provided the link earlier. The second thing that is needed is flexible and intelligent memory chips, interfaces, and controllers. So I will talk a little bit about that and also about cross-layer communication as well. So let's look into flexible and intelligent chips, interfaces, and controllers. So a keyword here that we find is like it's the in-field patching, which seems absolutely necessary going forward for the RowHammer mitigation or DRAM read disturbance mitigation mechanisms. So in this picture, you can see a processor, a CPU on the left-hand side, and a DRAM chip or module on the right-hand side. And these are different chips, different packages sitting far from each other on a motherboard. And there's off-chip communication here. And there's a lot of abstraction levels. And there's a lot of things that that prevent sharing proprietary data. There's a strict protocol in between them. So there are many academic proposals that proposes to put the DRAM read disturbance solution inside the processor, inside the memory controller. But DRAM chip is not there. It's in somewhere else. And this is something that you can plug in and plug out, right? The thing is, you need to configure your DRAM read disturbance solution based on the characteristics of this DRAM chip. And you configure it in your fab as Intel, for example, or ARM or some other company. And you ship out your chips. And then the user just plugs out and swaps the DRAM module to another DRAM module. So it can be replaced anytime, right? And it is actually being replaced in servers, for example, all the time. And now, based on the characteristics of this new chip, you need to reconfigure this mechanism. Or another thing is aging can change the characteristics of this chip. Now you need a reconfiguration. And therefore, deployed solutions should be patchable in the field. But we do not see that with the counter-based solutions, for example, because you cannot add more counters to a solution in the field after it's shipped. Okay. Interfaces should be more flexible. For some reason, my computer is not charging. It's going to power off sometime soon. Could you check the... It's not that one, the other cable. Anyway, I'll just continue as much as it goes. So memory controller decides what should be done and when here. And DRAM chip has read disturbance solution inside, let's say. And it consists of some tracking component and a prevention component. But the thing is, in the strict protocol, memory controller has fine-grained control over what DRAM chips does at every nanosecond. And the memory controller should provide the DRAM chip with necessary time window to perform these preventive actions. And there are some improvements in the JEDEC standards like RFM to provide this, but they seem quite primitive still at the moment. And the memory controller, and the reason is that when you give this time window, you need to have some understanding of like when this is needed and how much time does DRAM chip needs this. But there is no communication that comes from DRAM chip back to the memory controller that conveys this information. So the memory controller does not have this tracking information. Tracking is also in the DRAM chip. And as a result, this mechanism does not really work in an ideal way. So communicating is not straightforward due to strict communication protocol here. And we definitely need a more flexible interface or make the current interface more flexible. Let's go to the memory controllers that are intelligent in detecting malicious activity. So DRAM chips become more and more vulnerable to RowHammer and RowPress. And the key insight that 1,000 activations are enough to induce bitflips today with a combination of RowPress and RowHammer. And benign applications perform as many activations as this amount. And the problem is that DRAM read disturbance solutions are getting prohibitively expensive. So it's important to identify the malicious threats and processes and users in a way that we will not hurt the performance of the benign applications. Therefore, we need more intelligent detection mechanisms. And for example, AI can help. We can find some smart solutions as well. And there's a key insight here as well. The memory controller observes all memory accesses. So it has the ground truth. And it can be leveraged. So it means that more intelligent memory controllers can help us reducing these overheads. So that was all about flexible and intelligent memory controllers. Does that work? I guess it works. Perfect. Thank you very much. Behind the scenes, we had a very good collaboration here to find a working plug. So let's move on with the last point, cross-layer communication. So we have some abstraction layers in our systems. On the top, we have the software. We have the coder here. And not only the human, of course, there's some system software. There are some programs running over there. The types of operations that we perform here are around in the granularity of like memory allocations. We can create different memory access patterns, and we can create some control flow patterns. and we can measure time and power from the system level or software level. And but this is the control that we have on the system in this level. In the microarchitecture, we have a more finer grained view and control of the system. We can manipulate the memory request scheduling, for example. We can play with speculative execution. We can do prefetching, branch prediction, all those things. We can manage power in a finer grained way. And that's what we have at this level, right? But unless we go down to the device level, we actually do not have the bitflips. Bitflips occur in the device level. It's not in the microarchitecture or software level, right? It just propagates back to have implications on those levels. And memory isolation is also broken in the device level. So we have the ground truth data actually about detection in the device level. And from the software level, a lot of things are actually obfuscated. And you can see in the academic literature that there are a lot of solutions to RowHammer proposed in the early years that are in the software level so that they can easily deploy just, the patches or the solutions with a simple software update. But for each solution, pretty much, you can see a new attack that bypasses it. So, and their problem is in the detection, actually. Detection is not really good in software because we do not have a comprehensive and detailed understanding of what is going on in the system in the software level. And as we go lower, actually, we have a better view. But the thing is, mitigating the DRAM read disturbance in the device level is extremely hard because we do not have much control on the operations that we perform at every nanosecond, for example. So if you're in the DRAM chip, memory controller dictates what you need to do. So you cannot do anything inside the device, right? Unless memory controller allows you to do. And in the microarchitecture level, we have more things to do, of course. But again, we are limited by some strict protocols over there as well. But when we move up to software level, we can even kill an application or ban a user using a system or take more drastic actions as well. So in terms of mitigation, it works on the opposite way. So we definitely need a cross-layer communication going forward. And we need to observe the ground truth effect of read disturbance in the device level and perform our countermeasures, mitigation mechanism or proactive actions, preventive actions in the higher levels in microarchitecture or software, system software or application as well. But we need to convey this information from detection to mitigation. And it is not very straightforward today. And for that, again, we need a more flexible communication protocol again, and also better cross-layer communication across all these levels. So with this, I'd like to remind the thesis statement again. And we covered the second part of this thesis statement. And for the first part, I will again refer you to the previous talk. And this is the end of my talk. Thank you very much. Thank you for bearing with me for 2 hours. I can have more questions if there are any. There are also no silly questions. Just saying.
No question.
If microarchitecture level has information about both, so why not implement only that? Why do you need that?
So far what we did is like implementing things in the memory controller actually, right? But in BlockHammer, for example, we had that challenge that we didn't have the information about the raw address scrambling inside the DRAM chip. So that was one example. There are some mechanisms that, so for example, HiRA is observing the activation counts in a very accurate way and performing the mitigative actions, and it's also implemented in the memory controller, but it needs to maintain a lot of metadata, and there is a lot of overhead of that metadata storing in the DRAM chip and then fetching to the cache. Sorry, not cache, like the specialized cache in the memory controller. Fetching everything creates some overhead over there as well. So some other mechanisms implement a lot of counters in the memory controller. So that is also something critical for the patchability. So for example, there is a mechanism called graphene that comes up with a very good detection mechanism based on some Misra-Grease algorithm, frequent element detection mechanism. So it implements a lot of counters inside the memory controller, and you need to define the number of counters based on the vulnerability level of your DRAM chip. And once you swap the DRAM chip or your DRAM chip gets older, then yeah, you need to update it accordingly. But if you deployed your processor already, you cannot add more counters on top of that, right? But if it would be some software level solution, you would just like allocate a little more memory, you can easily patch it. There's more flexibility over there.
At a security perspective, like would there be any problem if you communicate too much information to processor?
That's a very good question, actually. Yeah. In terms of what security, I think it's not a problem for DRAM read disturbance aspect and that security. But for DRAM manufacturers, proprietary information, for example, for their competition in the market, they might not want to convey a lot of information back to the processor.
Again, that raises an important question, right?
Yes.
So in that case, DRAM manufacturers may not be on board with cross-layer communication kind of a solution.
Yes, I agree. Actually, there's some resistance on that as well, but we basically need to find the middle ground. And we need to convey maybe you can convey the information in an obfuscated way so that you cannot like gather information about their design or manufacturing process quality. I don't know. So, but there should be a way of.
No, like for example, even like information like XCPUS or what part of what rows are more prone to errors. If that information is known at processor level, can somebody exploit that? That is one aspect. Vendors not revealing too much information is one aspect.
Yeah.
But information about, let's say, which group of rows are more prone to errors, if that information is communicated at a processor level, can that be exploited?
Well, in theory, yes, right? Because when you expose that information, then maybe an attacker can also access that information and then target the attack to those like most vulnerable rows, for example. So you need to secure that information, yeah, somehow over there as well. I'm not sure if you would use like some enclaves or something like that. But yeah, so that information should be exposed to the, let's say, the system software, or like, I don't know, maybe some hardware components in the system that are not exposed to the user. Thanks. Yeah, it's a ongoing discussion actually. Yeah, I'm not sure if there's an easy solution for that. It's a very good point.
Any other questions? Thanks a lot, Giray.